Hello everyone and welcome back. Today we are deconstructing one of the most ubiquitous and formidable challenge in the world of system design. Think about the apps that dominate your daily life. What do Yelp, Uber, Swiggy, Zepto and Blinkit all have in common? On the surface, their value proposition differ widely. Yelp is for discovering that five-star hidden gem. Uber is for real-time logistics. Zepto and Blinkit are kings of instant gratification commerce. But beneath that sleek UI lies a unified architectural blueprint, the proximity service. Whether you are tracking a static storefront or a dynamic high-velocity delivery partner, the core engineering hurdle is identical. How do we execute a high-precision k nearest neighbor search across hundreds of millions of data points in milliseconds, say? In a high stake system design interview, the brand names are merely a cosmetic distraction, I would say. Whether your interviewer asks for a business discovery platform or a on demand ride sharing engine or a hyperlocal logistic tracker, they are all testing your mastery of spatial indexing. We should forget the rudimentary SQL queries that crumple under root. Today, I will try to explain you about the industry standard strategies like geohashing and quadtrees. So let's dive straight into the high level design for this service. Let's start with the proximity service now. So whenever you open an app like Uber or Yelp, the magic happens in milliseconds. You see drivers moving or restaurants nearby almost instantly. But behind that simple map interface is a complex distributed system. Today, we are going to deconstruct the proximity service, the engine responsible for finding the k nearest entities in a sea of geographic data. Whether it's finding a ride in a crowded city or a five-star dinner nearby, the underlying architecture remains remarkably similar. So basically, this proximity service is one of the favorite questions of the interviewers at good companies. And before you start anything about this service, you should know what this service or what this component actually does. So, what this component actually does. This is a major question. So basically what this component does is it finds us the k nearest entities. In case of Uber, it would be drivers. In Ola also it can be drivers. In Yelp it can be multiple restaurants which are within the range or the radius given by the user. So in this example, we would go with Yelp. So Yelp is basically an application where people can, give people have their latitude and longitudes, and based on their location, we find the k nearest restaurants, and basically the suggested restaurants are then visited by the users. So as I told about Yelp, uh, I would like to, I will call the restaurants as businesses over here, and basically we will find the businesses within a specific radius. In case of Uber/Ola, as I already told, we would find the drivers, given that we have the coordinates of the user. Yeah. So whenever we get this kind of questions, right, I usually have a delivery framework which I follow. So basically, what happens in a high pressure system design interviews or a real world sprint, we need a repeatable mental model, and I call it as delivery framework. This is mentioned across various sources, and I am just following that where we list down the functional requirements first, along with the non-functional requirements. Basically, this step is called as requirements gathering. After that, we go with listing the core entities. We design the API, and we also do the high level design. And after that, once we are done with the design, we move on to the deep dives. Yeah, so again, just quickly, just reiterating on the delivery framework where I just mentioned about the functional requirements, the non-functional requirements, together we call it as requirement gathering. We are listing the core entities, we will be listing the APIs, data flow is very optional, designing the high level diagram, and covering the deep dives. Yeah, so let's start with the functional requirements. Remember, functional requirements are the ones which can be discussed with the interviewer at the start, or if you have a brief idea about the problem statement, you only can just go with the functional requirements and have a understanding with the interview that you're thinking in a correct direction or not. In this case, I have written this three functional requirements, which I think are the three major pillars of this particular problem statement, where first we will be returning all the businesses based on the user's location and the radius mentioned by the user. This is a very important functional requirement in this case because our whole problem statement lies on this functional requirement. The second thing should be that the business owners should be able to add, delete, or update their businesses, which we would find on the application or the user would find on the application. The third functional requirement would be the customers, which when they click on particular businesses, let's say there is a customer who comes on the application, selects his radius, and based on his latitude and longitude, we find all the businesses near to him. Once he finds all the businesses, let's say he clicks on one of the business. So when he clicks on the business, we want all the information about the business to be loaded. I know in our case, let's say we have Yelp, where a user comes in, he just sees the nearby restaurants, he clicks on the restaurant, and he gets a detailed information about the restaurant. Yeah, so now let's talk about the non-functional requirements. Here, the first non-functional requirement for us in for our system would be low latency nearby business check. This is nothing but whenever the user comes on the application and he searches for the nearby restaurants or businesses, he should be able to get that data within few seconds. So our first non-functional requirement would be regarding that. Our second functional non-functional requirement is based on cap theorem, where we think about consistency or availability. What should our system follow? Because partition tolerance is anyways non-negotiable in this case. So in our case, we would be thinking about high availability, then consistency, because let's say even if a business owner adds a business, we would be okay uh, with showing up the business or reflecting the business on our application, let's say after 1 or 2 days, which is absolutely fine for us. But in but we want high availability, as whenever the user comes to our application, it shouldn't be down. So this is uh, the thing which we would actually go for in our case. We'll also see for the data privacy, and we should be uh, checking that if our data, whatever is present with us, should be GDPR compliant. So, a general point after discussing the non-functional requirements is about discussing the nature of our system which we gonna build. So here generally we see if the system is read heavy or write heavy. So in our case, or in general, the proximity services are read heavy because people search for the restaurants or the businesses far more often than the restaurant owners updating their restaurants information or the business information. This actually tells us that we need. Okay, so now that we have completed the functional and non-functional requirements, let's run the numbers to see the load we are dealing with. This is nothing but back of the envelope estimations or calculations. So imagine we have 100 million daily active users, and let's say if each user performs just 5 searches a day, that's 500 million requests, When you break that down, we are looking at roughly 5k queries per second. While 5k QPS is manageable for standard cluster, we should always remember that top tier platforms like Instagram handles millions. Our goal is to build a foundation that can scale from 5k to 5 million without a total rewrite, I would say. Okay, so now let's move on to the core entities. The core entities which we would have in this particular problem statement would be businesses and the users. So for every business in the list of businesses or our business table would have a business ID, a address, a city, state, country, and the two important things, which is latitude and longitude of that particular business. We'll also have some of the users, and a user will always have a user ID, his email, his phone numbers, and any other things which we would actually need to identify the user. So these are our core entities, and we should always remember that it's not necessary to list down all the core entities at the start. It's fine to revisit this part if at all you need in between when you are actually designing your architecture. After that, we can also move now to the API design, and we can list down all the important APIs which we would need to architect this particular system. So the first important API that we would need is the nearby API, where we would like search based on the latitude and longitude given by the user and also the radius specified by him. This particular thing is would be our search criteria, and this would be our request parameters in our URL. At the end, we might get a response based on, let's say, if we can apply pagination. We would not discuss too much about the pagination because it is not the scope of our problem statement as of now, but it is a good thing to tell the interviewer that you know that you can use pagination over here. If, let's say, we are having a limit of 10, we would be return the 10 nearest businesses and the business list, and every list would have the object as business object. The next set of APIs are basically the CRUD APIs for the businesses, where we would get the information about the business, or let's say if we want to post a new business, we have a API for it. And let's say if we want to update the business, we have a put API. We also, if we want to delete any kind of business, we also have a API for this. So these all set of APIs will actually help our system. Yeah, so now let's come to the high level design of this particular problem statement, where we have a user which will actually get routed by a load balancer to any of the service. So here we have a nearby service and a business service. So we are actually following here the microservices architecture, where the nearby service is being segregated with the business service, because both of them have different kind of loads. Here mostly nearby service would get a read load, while business service would get a write load, which will help us to scale these different services based on the type of load they are getting. Because let's say if we are updating a business's phone number, which would actually slow down the search engine used by millions of the users, so we separate these concerns to ensure the fault tolerance. Alright, now that we are done with the high level design, we'll move on to the last part of our delivery framework, that is deep dives. And now we are getting to the meat of the problem, that everything we have discussed so far, the APIs, the requirements, the scale, all of it relies on one single critical question. How do we actually find those nearby businesses in real time? On the surface, it sounds easy. You have a map, you have a user, just find the dots close to them. But mathematically, this is a spatial search problem. In a world with hundreds of millions of data points, searching for neighbors is an expensive operation. If we don't solve this efficiently, our app won't just be slow, it will be unusable. This is the make or break moment for any proximity service, I would say. We are going to look at two ways to solve this, and the first one, which comes to mind of most of the people, is standard SQL approach, and the other one would be geohash approach. All right, now let's move on to the SQL strategy, and I'll also tell you the reason why I'm calling it a 1D trap. Okay, to write a query, we first have to speak the database's language. Our user gives us a radius in kilometers, and but our databases stores the locations in coordinates. So how do we bridge that gap? On our planet, 1 degree of latitude is approximately equals to 111 kilometers. So if we want to find a 1 kilometer radius, we simply divide 1 by 111, which gives us approximately 0.01 latitude. This is our magic number now. To create a search area around our user at 40.71 and minus 74.00. These are basically our user coordinates. So we need to create a search box, or we call it as a bounding box. We basically add 0.01, which was our magic number, to the latitude as well as longitude to get our lower bounds and upper bounds. So if you see over here, if we subtract 0.01 from 40.71, we get 40.70, and if we add 0.01, we get 40.72. So similar thing which we do it for longitude as well, we get this minus 74.01 and minus 73.99. So when we start writing the query, we have this particular query where we have select name from the businesses, where latitude is between the particular box and longitude is also between that box. So once we have this kind of query, this on the surface, this is perfectly logical. We are asking the database to filter two columns at once. But in world of high level system design, this is where we hit a massive bottleneck. And here is what how actually our database is going to look at it. So when we fire this particular query, we see that the Starbucks uh, is the row which gets filtered out. But with the Starbucks row, we also get this random named restaurants row as well as uh, with that filtered, which also gets filtered out basically. But if you see, it is not in the longitude range. That means the first our database would have actually filtered out all the latitudes which are in this particular range, and after that we are again filtering out the longitudes. So if you see, this is a strict order of n complexity problem where we have to scan the whole database uh, and then get all the businesses which are within the search radius given by. Okay, so let's summarize the strategy we just walked through. We have our user at say 40.71 and minus 74.00. To find the businesses within a 1 kilometer radius, we applied a magic number of 0.01 to create a bounding box. We then fired off our SQL query, which was select name from businesses, where lat is between this particular two numbers and long is between this particular two numbers. On paper, this query looked clean, logical, but in production, this is where wheels fall off. Here, the under the hood reality of how this query works is based on how our database is just a one-dimensional thinker. First, it checks the latitude range, which is over here, and then it uses the index to find every single row between 40.70 and 40.72. So in our example, Starbucks and random was considered out of the filter which we had, and after that the longitude was also compared. So if you see over here, for every single one of those filtered rows, the database must perform a secondary check for longitude range also. This is a bottleneck. The database is doing double the work because it cannot filter both dimensions simultaneously. Now, if we also look at our back of the envelope calculations, we estimated that our system needs to handle 200 million businesses. So in a databases of that size, a latitude strip of 0.02 degrees could easily contain 500k to 1 million records. And this will surely be a very slow query, I would say. And this leads to a massive spike in CPU usage and disk IO as well. Our latency will skyrocket from milliseconds to second, and the system will eventually time out. This is an order of n complexity in world that requires log n speed. Now, to tackle the problem of 2D coordinates, we have Geohash. So this hash works by reducing the 2D longitude and latitude data into 1D string of letters and digits. It works on recursively dividing the world into smaller and smaller grids with each additional bit, so that our planet is divided into four quadrants along with prime meridian and equator. So how it works is we have an algorithm for it where we have defined the ranges for latitude and longitude. For latitude it is minus 90 to 90. For longitude it is minus 180 to 80. Minus 180 to 180. After that we do a binary search partition for each coordinate, and based on the search space, if it is greater than mid it will be a bit 1, else it will be a bit 0. We repeat this process till 15 times, because say if we want to have a 6 byte precision for geohash, we would do it for 15 times each for latitude as well as longitude. In this way we'll have those 30 bits. After the interleaving of that 30 bits, we convert the whole thing into a base 62 encoding where we group by 5s, and then we finally have the geo hash of that particular longitude and latitude. Yeah, so if you would have not understood the algorithm, which is perfectly fine because I have got the example for the same coordinates, that is 40.71 comma minus 74.00, we will calculate the geo hash for this particular coordinate. So we will be having at the end, once we complete this algorithm for this coordinates, we would be able to generate a hash for this two coordinate. And the algorithm which I mentioned just before this is used to get that hash. So initially, as I told you, that we will be having latitude calculation as well as longitude calculation. So our latitude lies from minus 90 to 90, whereas longitude lies from minus 180 to 180. So initially what we do is, as our latitude lies from minus 90 to 90, the midpoint is 0. And if the coordinate is greater than the midpoint, we will simply have bit as 1. Okay, after that, once if the bit is 1, then we will actually reduce the search space, which now it becomes from midpoint to the higher point, which is 90. So it will become 0 to 90. Again we calculate the midpoint, which is going to be 45. We'll check if 45 is lesser than 40.71, which is not, so that's why we would say bit is equals to 0. So we just have to remember that if midpoint is greater than the coordinate, then the bit would be 0, otherwise bit would be 1. So similarly we do it 15 times for latitude as well as longitude. So we get, at the end we get a 15-bit array for both latitude as well as longitude. So if you see over here, we have 10111 for latitude, and 01001 is the bits array for longitude. Once we are done with these arrays, once we are done with the calculation of this particular bit arrays, we interleave this both strings. So we can call it array, we can call it strings, whatever we want to. So once we have got the strings, we interleave the strings. Now what do we mean by interleave is that we take one string of longitude and one string of latitude respectively. So if you see over here, 0 is taken first, then we take one character from the latitude string, which is 1. So we have taken 1 over here. Again we go with the longitude's second character, which is 1 over here, and 0 from latitude. So if you see, we have 1 0. So similarly we just interleave both the strings, and then once we have interleaved both the strings, we get a 30-bit string at the end. Once we have the 30-bit string, what we do is we group it in fives, because base 62 obviously has 5 bits because it is 62 base 62 encoding. Once we have got the 30-bit string, we encode it in base 62. So first of all we convert those, we group those into uh, five groups, and then we convert it into decimals. So this particular 01100 is basically 12 in decimals, and 10111 is 23 in decimals. We convert that into base 62. 12 is basically D in base 62. 23 is represented by R in base 62. Once we are done with all these things, so if you see, our final geohash would be dr5rmw for the coordinates 40.71 comma minus 74.00. So now if you see, our coordinates which were two-dimensional are converted into a string, and this is what the magic which goes behind this geohash algorithm. Just 2 points to note about GeoHash is that Geo has 12 precision levels. So precision factor actually determines the size of the grid. So here, if we have, let's say, a 6 sized hash, it would be more accurate than 4 sized hash. So if I just talk about the rough figures, if we have 0.5 kilometer radius, it is roughly equal to 6 geohash length as well. And if we talk about 20-kilometer radius, it will be 4 geohash length. So basically, the higher or the longer the length of the geohash string, the accurate the grid size is. So the deeper we move into any kind of map or any kind of geographical data, the higher or the longer the length of the geohash is. Now, before wrapping up this whole geohash topic, I would actually like to explain you guys about one of the famous DSA question, which is related to what we just learnt about. That is interleaving strings, which is on lead code and is a very good question. And in the lead code version of it, we are given two strings and asked if the third string can be formed by weaving them together while maintaining the original order of characters. It is labeled as hard problem because it usually requires dynamic programming to solve for all edge cases. But if we look at how we just used it in our proximity service, we didn't just interleave the strings for fun. Our S1 or the string S1, which will be given in the lead code, is the latitude sequence, and S2 would be a longitude sequence. The resulting S3, the interleaved string, becomes our geohash. So let's jump on to the lead code question, what we have got, and maybe I'll explain you this thing once again. Let's start with the problem, which is on lead code interleaving string. So here also, if you see, we have been given two strings S and T, which I mentioned earlier, where we just need to see if S3, which is there given to us, is a interleaved string of S1 and S2 or not. We just have to return true or false at the end. So if you see over here, and the thing which we talked about in our geohash problem was we were interleaving the strings or weaving the strings one by one. Let's say if this was the longitude string and this was the latitude string, we were taking one by one characters. But in this problems, we can have more than one characters also being interleaved from the both strings. So here we just have to return true or false. So, and also if you see over here, the standard string lengths are being given as 100, and the S3 is obviously 200 because at max both can be 100. So interleaved string would be 200 length. So we have been given this problem, and by seeing the constraints only, you would get to know that this is something where we have to try the possibilities and get the answer. So the thing which we would actually use over here is dynamic programming, and the way I think at it is mostly with respect to solving this string problems into 1D one based indexing. So what I generally do is I extract the lengths of the particular strings initially only. So that will be, so I'll call it as n1. It will be s1 dot length. I'll quickly calculate the s2's length as well. I'll also let you know what my intuition is behind this kind of problems. So int n3 is equals to s3 dot length. So now that we have all three links length, what I would do actually in my case over here is, uh, let's say we have S1 and S2 over here, right? We compare the last characters, which is C and A, with the S3's last character. So if you see over here, obviously one has to match. So in this case, C, either if C matches with the S3's last character, which is also a C, then we would actually tell the recursion to solve for this particular string till this length and S2 as like whole length, because in recursion what we generally do is we solve a bit of the problem and the rest problem we give it to the recursion itself to solve it by its own and return us the answer. I'll explain you as in we write the code, because the code will be quite intuitive, because I'm writing a recursive code for this first, and then we'll quickly memorize it and we'll see if the solution is working or not. So initially I will just have a function, a recursive function, which would take the input as the lengths or maybe the last indices of the all three strings. So let's say I have this, I have s1, I have s2, I have s3 as well. So I've got this function which will basically return my answer. So this will be a bool f. I will just have int I, int j, int k. Okay, and I will pass it by reference all the strings so that we are good with the memory as well. S3, yeah. So now that we have given the problem, we are given the recursive function which I'll be solving. So initially we assume the base case first. So in the base case we generally think of the most basic case which might happen with this problem, where let's say all the three strings have the length as 0. So if the lengths are 0, then obviously our I would be 0 and j would also be 0 and the k also would be 0. So in such cases obviously we have to return true, because empty strings will always be interleaved. So I just return a true in such case, and this becomes my base case for this particular recursive function which I've written. Okay, now let's write the conditions. So let's say if I have, because it's one base indexing, right? I will be having this check where, and firstly I'll be checking if all of my three strings indices are greater than 1. So this is how I check it. So once I have this check, now I'll be checking because I'll be going from bottom, I mean the last of the both strings, and comparing with S3. So I would have two cases. Either my both, let's say S1 would have, S1's last character is C anyways. S2's last character, if it would have been C, then we would have been in dilemma that which one to consider. S1 should be considered or S2 should be considered for interleaving. So in that case, we would actually, return, uh, we'll try to recurse on both the strings. By that, what I mean is when I write the code, you will get it better. Is, let's say I have a S1 of, let's say I minus 1, I would say, which is equals to S3's k minus 1, which is the last character of S3, and and S2's, which is j minus 1, is also equals to S3 k minus 1. So if this condition is true, then I basically what I would do is I would try both the possibilities. I would say that return where f, so what I would do is, let's say I will try for the first string and the third string. So basically S1 and S3 I'll be trying, because C matches in the last characters of both the strings. So I would say that reduce I minus 1, which will be like I'll ask recursion to solve for the strings length, which is one lesser than what we have right now. So immediately we would pass on I minus 1. We would pass j as it is, because we are not decreasing the length of s2, because we are thinking that we'll try it in the second case. So here it would be I minus 1 comma j comma, we would also have k minus 1 over here, and then we'll be passing s1, s2, and s3. So this is my recursive function. We would try the other possibility as well, where we would not consider, still if we here, because I'm saying that here also we would have a c, right? So if both the cases have c, still we would not consider s1, because in this condition we are already considering it. But in the second condition we would consider s2 and s3 as interleaved string, and then that's why we would pass I as it is, but we would pass j minus 1 and k minus 1 here. So whichever actually returns true will actually return the whole parent as true. Okay, so everything will come out as 2 here, true here. Yeah. So we have got this particular case now. Now let's say only now the other two cases would be where only one of the characters only matches with S3. Okay. So here I would say that I am just checking for I and K, and obviously this wouldn't be here. I would just say that return for this thing. If you are able to return a true, you return true. If you are returning a false, that is also fine to us. So similarly, what I would do over here is I'll just copy this once again. Now the next time, which is over here. Now if you see, actually the existing case which is given, C and C matches. So what we say that you just solve for this part of the S1 now. That's what I have given over here, I minus 1 and k minus 1. Okay, and j is as it is from here. So still, so this is how we reduce the length of the strings if it matches. So similarly, now we would have the second condition where it is j minus 1 and k minus 1, where if the second string matches with the second string's character matches with the third strings character, which is, so here we would have this case where s2's character matches with the s3's character. So we've got this. Okay, we have actually solved this part, and at the end, if nothing matches, then we would say it is a false. Okay, so I have written this recursive function. I know we need to memorize this as well, but we'll just see if the test cases are running fine or not. Let me just make it single t. I'll just see if test cases are running fine. I'll just quickly memorize it if everything runs well. Okay, so this looks fine to me. At the end, I would just memorize this particular thing by having a 3D vector. Okay, and I will be passing this. I just memorize it by just passing the DP array into it, and uh, one second. So I have this, and now I've got just the final check. I'll just copy the snippet which I already have. So if you see, I have just memoized this particular part. I'm just checking if that thing is present in the cache, just using the cache now here, just saving. This is the saving of the cache and this is the usage of the cache. I'll try to run this now. We'll see if this works. And yes, I think it's accepting. We'll just submit the solution. We'll see if this interleaving works or not. Yeah, so if you see, this solution has been accepted. So now let's visualize this geohash thing, whatever we have learned. So I'll just explain you how this abstract math of bits and grids is visible in the visualizer. So here, uh, as we have done the all whiteboard things, let's see how the things work in action. This is the geohash explorer and it's the best way to visualize how we have partitioned the world. So if you see over here, the map is divided into large rectangles, each labeled with a character D, 9 or F or whatever you are able to see on the screen. So if you remember, we had that particular Starbucks business location, right, which had the coordinate as minus 40.71 comma 40.7 comma minus 74, which we took the geohash, which was D. So when I write D over here, right, it immediately focuses on the D block. And then if I like start writing the hash which we calculated, it will try to zoom in. So once I write R, which was the calculated hash, it will again zoom in into the R part of that particular box. So if you see, we are moving towards our location or the coordinates. So again, the next character was 5. So immediately we moved on to the 5. And now in this 5 block, if you see, our next geo hash was R. So if you see, again we are moving towards the New York location. So as in, when we extend this geo hash, as I told you, there are 12 precision levels. So if you reach till like 12 characters of a geo hash, you will be able to exactly pinpoint the location which you are referring for. So if you see over here, whatever locations are there which are nearby to this particular DRFR would have the same prefix. So in SQL, essentially, when you were writing initially, where you're comparing the latitude between this particular two numbers, basically, which you used, and for longitude also you were comparing between the two numbers, and we essentially thought that it was order of n complexity problem, which we then reduced that particular 2D dimensions into one dimension by converting that into a geohash. Now, whenever we write a SQL query for the nearby locations, we would just write select business from uh, the geohash, and we will use the like query for that, so that all the strings which have the start as drf dr5r would, all the businesses which have the same geohash would return to us. And if you see over here, if we zoom in, so if you see all the locations which are nearby, because all of them would have the same prefix, the geohash for this particular part would be dr5rb. For this it would be dr5rc. So essentially these two locations are nearby locations. So this is how actually geohash work. But there is some problem also. These geohashes are not very perfect. So there, if you see over here, if you carefully see over here, uh, we have a bit of problem with the boundaries. So if you see over here, uh, here if you see the boundary of this particular hash, let's say dr5r, right, if I just remove r, we are essentially here. So basically, even if these two particular locations are very near, if you see my cursor over here and here, but both belong to different hashes, and this is what makes a problem with geohashes. But how intelligent engineers solve this problem is by taking the nearest neighbors out of it. So first of all, what we do is, whenever we are given any hash, let's say this is dr5, so basically dr5 represents this block. What we do is we calculate the neighbors of this particular block, that would be 6 7 k h 4. We calculate the 8 nearest neighbors. So if you see whatever the neighbor it would be here, we just calculate them as well and take them into consideration also when we are calculating the nearby locations, so that we don't miss out because of the boundary conditions. So if you see, I'll just explain you how we will go inside. So we had the hashes dr5r, and then after that, if you remember, we had mw. So if you see how precisely, if we go inside, we are able to locate a particular coordinate or location very nicely. So if you zoom out, if you see, this is the place we were actually referring to. And if you see, we can still go till the sixth seventh level over here as well. So we can, as I told already, that we can go till 12 precision level. So basically this visualizes are very useful for us to understand how things works in terms of geohash. So you guys can also use this visualizer tool to understand how geohashes work. You can also try to see if how we can actually solve the boundary problem. As I told you that the boundary problem can be easily solved by taking the eight nearest neighbors, or this the nearest neighbors for this particular block. If I just zoom in, right, if I continuously keep on zooming, because our geohash is a seven length geohash. So basically, if you see, if you want to just take any, let's say for this p, then you would just take the eight boundary hashes also into the consideration, and you will see the nearest locations for this based on the whatever we have the radius given by the users. So I hope this visualization was helpful for the viewers, so that they can understand how basically the geo hashes work, and how they help us in calculating the k nearest neighbors.
Yeah, so let's discuss the final flow now, as we have completed the geohash topic, where we have seen how geohash is helping us improve the time complexity of the query, where we have now gone from order of n to order of log n, because most of the modern DBs use B trees for string indexes, and for the queries like where geohash is like, and where we have the regular expression for it, this can be achieved in order of log n or order of 1 times. So just to have a final flow where what user does and how the system would work, here are my 4 to 5 points which I have written over here, just to summarize what we are going to do. So initially, let's say there is a user who comes to Yelp, and he finds and he wants to find a restaurant within 500 meters. So basically the user would send us, we would get actually his location, the latitude and longitude. Let's say I have taken some sample latitude and longitude, then the load balancer forwards the request to the nearby service which we had, which we have also shown it in our uh, high level diagram, where this is the nearby service. We also have a business service that is for updation related to any client, any business related data. Basically this is for business users, business owners, I would say, and this is for the normal users who are going to use our application. Okay, so once we are done with that, then we then based on the user location and the radius info, the nearby service finds the geohash length that matches the search. For example, for 500-meter precision, because he is asking for 500-meter, that means we will need a geohash length of 6 over here, because as I told you, if we increase the length of geohash, it becomes more precise, as we have also seen in the visualization portal, right, where we just saw that we as soon as we increase uh, the length of the geohash, we were able to deep dive into the geographic map which we saw, right. Then after that, the nearby service will also calculate the nearby geohashes also. This I told you because we would be having the boundary problem, right. So based on the boundary problem, we also find the neighboring 8 geohashes also. So at then finally we would have 8 plus 1, 9 geohashes, for which we will be finding the corresponding business IDs which are near to them. Okay, so this will be our first geohash, and the neighboring 8 geohashes actually will be also added into the list. So for every geohash we'll be running this particular query, we'll be getting the businesses, and all the businesses which are gathered using all these geohashes will be returned to the users. Basically those are the businesses or the restaurants which are within 500 meters. So another popular solution is Quadtrees. Just like we discussed about geohashes, Quadtrees is also one of the solutions to solve this particular problem of getting the businesses within the specified radius based on users' latitude and longitude. So what is a quadtree? Quadtree is a data structure that is commonly used to partition a 2D space recursively subdividing into 4 quadrants every time based on some criteria. Now what is this criteria can be anything, but in our case, let's say we would say that if the number of businesses within that grid exceeds 100, then we would divide the particular square into 4 quadrants. Now when I explain you with
a example, it will be more clear to you. This is an in-memory structure, by the way, and it is built at the startup time of the server. Let's say we would be having a nearby service, right? In that, whenever the server of that particular service starts, this quadtree can be created. Now let's say in our case, I'll not take 100 as my number of business when it exceeds to, which is my criteria to divide the grid into four quadrants. Let's say I consider it as 4 as of now. I mean, my criteria is 4. If the number of businesses exceed by 4, then I would say that I need to divide my grid into quadrants, 4 quadrants. Let's say I have a business over here in my quadrant. This I would assume to be my earth, okay, this particular square. And let's say I have one business over here, and let's say again I have one business here and one business here. Now we have 4 businesses in this particular quadrant, and let's say there after some time there is a fifth business over here which comes to my grid. Then what happens over here is it has exceeded the number of businesses which are acceptable in my criteria. So as in it exceeds the number which I'm having right now, which is 4, and in this case now there are 5 businesses. I'll immediately divide my grid into 4 quadrants. Okay, now these are all my individual grids. Now once again, let's say in this particular grid somehow the businesses exceed again by 4. Okay, as I have added 5 businesses over here, again this particular square, a particular grid gets subdivided into 4 parts. It will be equal. It is not looking well in this diagram, but it will be like equal 4 quadrants in this particular grid, if you see. Okay, so this is how quadtrees work. So how these are I mean, I'll not say better. How this are, compared to geohashes are that this I would say that geohashing is great, but it has some flaws. It is static. In a geohash system, a grid square in a empty Sahara desert is exact same as a grid square in, let's say, downtown Manhattan. So in Manhattan, that square might have 5,000 businesses, but while in Sahara, square has 0. This leads to unbalanced data. If we want to be truly efficient, we need a system that adapts to how crowded an area is. That's where quadtrees are coming into the picture. Okay, so the main thing over here is we have to create a quadtree every time, and we will so how it happens is, let's say you will be initially you had a grid and now it has 4 children, right? Once you are having more than 4 businesses, right? Again, if you see, this particular grid got subdivided into again 4 parts, right? 4 quadrants. So again the tree would look like this. So initially we usually name this particular quadrants like this is northwest quadrant, this is southwest quadrant, this is northeast quadrant, and this is southeast quadrant. So every time, let's say there would be all our leaf nodes will be having the businesses actually. So in our case, this 2 businesses would lie in this leaf node, this one business would lie in this one leaf node, the other one here, and respectively all the businesses would be in this particular leaf node of this particular grid. Okay, so here anyways we just have one businesses, so here both all of them are leaf nodes. So we have to remember that leaf node has always lesser number of nodes or equal number of nodes than the criteria we have defined. So in our case the criteria was having 4 businesses only in a particular grid. If it exceeds, then we have to subdivide that part recursively and create 4 quadrants once again. So this is how the quadtree is created. So whenever you do a search on this quadtree, it will be always a login quadtree, I would say. Login time complexity, I would say, to search anything in this particular quadtree. So again, taking the same example of the coordinates which we had in all throughout this video was 40.7 comma minus 74.00. So what will happen is every time, let's say for this
coordinate we are searching for the businesses which are within 500-meter radius, what we would do is we will every time ask the particular route that does this coordinate lie. First of all, it will ask the route that is it a leaf node. So in our case, if you see over here, it is not a leaf node. So we just have this nodes as leaf nodes over here, as I have already drawn this quad tree. So if you see over here, the root is not a leaf node. So we again go down and ask the four childrens, does this particular uh, coordinate lies within them or not. So let's say that it lies within this particular coordinate, which is which this particular coordinate, which is NW. So we again go to this particular node and ask if it is a leaf node or not, and it says that it is not a leaf node, and it will redirect us to the four nodes, which four children basically whatever it has, and again those children's names would be NW, and E, SW, and SE. Again, if you see over here, let's say it comes to NW and NW is a leaf node, we'll again ask, does this coordinate lie between in NW, I mean the businesses which are there in NW or not. So basically what we have done is whatever the businesses which we have are spread across this leaf nodes now, and whichever leaf node actually contains our business, contains our coordinate, right, which we are mentioning, we go into that particular leaf node and we then use the Haversine formula, where it is just like a distance formula, where we get the businesses which are near to this particular business and are having a radius of less than 500 meters. So here basically the advantage we are getting is that we are moving to the leaf nodes, and the nearby businesses are in those leaf nodes only. So whatever leaf nodes which are within the 500-meter radius will be filtered out, and this is how we would get all the businesses which fulfill our criteria or the users criteria. So let's do one DSA question which is similar to the concept what we have discussed just now, which is constructing a quad tree. This is a famous question asked in many interviews, and I think this will make you feel quite comfortable in how actually quad trees are created inside the servers what we have. This question on lead code, which is construct the quad tree. So here it is also the same thing what we have discussed in our notes previously. This is just a question which has been asked in multiple companies, which I have seen till now, where they ask you to construct the quad trees based on the matrix what they have given. So if you see the criteria, as told you that if we want to divide a particular grid into four quadrants, there has to be some criteria. So in this question there is some criteria. I know we have discussed about a criteria where, let's say, there are more than four businesses, we would definitely divide the grid into four quadrants directly. Here the criteria is bit different. Here it says that if at all a particular grid has uh, different numbers, then we have to divide the particular grid into four quadrants. By that what I mean is, if you see this whole grid, it has one and zeros, which definitely makes this grid being divided into four parts, because it is not satisfying the criteria, where criteria says that a particular grid should have only same value of all the no, all the cells which are present in that particular grid. So if you see over here, one and zeros are, if you look overall grid over here, we have one and zeros, which is not acceptable according to our criteria. So we have to certainly distribute I mean subdivide this matrix into four quadrants, which we have done. Again, we see for this particular matrix or this grid, if you see over here, all are ones, so which is good. We don't need to subdivide this particular matrix. Again, if you see this one, which is the southwest grid, where all are ones, so no problem. Here also there are all zeros, which is also not a problem for us. But here if you see, we again see zeros and ones, so there has to be a subdivision once again in this particular grid.
as you can see in my through my cursor, for this particular grid we have to subdivide, and we have rightfully subdivided that matrix into 4 quadrants once again. So again, if I see this particular quadrant, all zeros, which is also okay, again here all zeros, which is also okay, here all ones, which is also okay, all ones, which is also okay. So now that we have got this understanding of how the quadtree should be created based, and the criteria also I've explained what is the criteria in this case of the problem given on the lead code. So based on that, we just have to return this kind of quadtree at the end. Okay, so we have been given a basic structure of how the node should look like, and then we just have to return a tree like this. So if this is particularly a leaf node, if you see, because based on criteria is satisfied over here, all are same values within the same grid, all cells have same value, here also all same cells have same value, so this is a leaf node. This was not a leaf node directly because the zeros and ones were there in this particular thing. So we subdivided this matrix into uh, again 4 quadrants, and then once we subdivide that, the quadrants had the same values. So now this is satisfying the criteria. Okay, so we are calling it a leaf node. So that's why if you see over here, the leaf is 1 for this, again is leaf is 1, again is leaf is 1, again is leaf is 1. Okay, over here, but here if you see over here, isLeaf should have been 0. Here I know it has been given 1, but the problem statement also says that it's fine to make it as isLeaf uh, uh, 1 as well. So there, if you read the problem, you'll get to know that there is no problem in marking that isLeaf 1, though it is not a leaf node. Okay, so though it is sorry, it is given, isLeaf is given over is 0 over here, I'm sorry for that. So isLeaf is 0 over here, and the value is 1 over here. The isLeaf is 1 over here, which is okay. This is also easily, this is also easily, so this tree is perfectly fine. I'm sorry for that. So we'll start again by creating the matrix. Okay, I mean the quad tree. Okay, so we have been given a grid. So what I do is I'll just extract quad the size of the matrix, which would be, sorry for that. So quickly we'll just start writing the code as well for this now. Let's say I will have a function f which will accept the initial r comma c and the ending r comma c of this particular grid. So it will be n comma n, and certainly I'll be passing the grid to this function. And yeah, so I'll also show the recursive way of solving this question we'll be getting. So what our function would be, it will be returning the root of our quad tree basically, right? So I would say it is int I comma int j int n comma int m, and we are also getting a grid. Okay, I'll pass it via reference so that we don't end up with a memory issue. Okay, so now what will be our base case? So if we properly think about our base case, it would be if the n minus I would say, if is equals to 1, then that means we just have one square. Okay, we just have ended we have ended up on a square whose size essentially is just 1. So that is obviously a leaf node, because all the nodes in that so if you see over here, this, if we end up on this particular square where the difference between the n and I is just 1, then we are saying that we are landing up on a cell which has just size 1, and obviously it will be a leaf node. So we'll be returning that node there itself. Okay, so it will be, and also if you think about base cases, we just think about the basic case initially for the problem. Let's say we have just given a grid of size 1 cross 1. What will you return? You'll just return that particular node, right? So I will also do the same thing. I'll wrap that data into the node where I would say it is a grid. The value inside that node would be grid I comma j. Okay, and it will be a leaf node for sure. So I'll just return it or true. Okay, so so we have a constructor for this, okay, where we have the value and we have the leaf. So if it is if we just have the value, other all the four nodes and the four children would be anyways null for this case. So we have completed the base case. Now let's move on to check if there now we have to check for the criteria, right? So let's say I have one function where I call it gives me a bool comma int, I would say. I'll tell you what it will do. Basically it will just tell me if it is a leaf node, and basically what is the value of that leaf node. Because if you see here, the leaf node has value 0 because all the numbers within the grid are zeros. Here the leaf node has value 1, so basically we have to also return the value whatever is inside it. Okay, so I'm going to create one function, let's say a check leaf function. Okay, check leaf function where I have got I comma j comma I'll pass n comma m comma grid. So in the interest of time, I'll just copy this particular leaf check leaf function which I am already having. I'll also explain you that as well. So if you see, I will just iterate over the whatever the matrix I have, which is the first r comma c and the ending r comma c, basically the grid start index. So this will be, let's say this will be the start index at the start, and this will be the ending cell at the start. So this coordinates will be having this coordinate and this coordinate, start coordinate and end coordinate. Then we will just iterate on this particular thing, and we will see that if all are zeros. So if all are zeros, then we would say that the value is 0 of that leaf and it is a leaf node. Okay, so the flag will just turn to 1 if all are not 0. Again we'll check for 1. I think this is a very basic code. We'll get to know at the end if it is not a leaf node, we will call it a false, and the value can be anything. Okay, so if it is not a leaf node, then obviously we don't know, it can be 1 or 0, so we are just returning 1 by default in this case. So I've got this particular thing over here now, right? So now what I will do, I will try to create a leaf, I'll try to create a node now. Okay, so this would be, sorry, so what I will do, I'll just again copy paste some part of the code. So what I will do is, now I will calculate the root node, what it would be. So if we would have got a leaf node, let's say the first node, I mean, let's say all this matrix was all ones, then we would have got it as 1, the value as 1, and it would have been leaf as we would have got the true value, right? So now that we will be calculating the root based on the values we have got from this particular checklist function, and we will be creating the root. So if the root is not null, if the root has, the root itself is a leaf node, then what we will say that we'll just be returning a root. Otherwise, what we would say that we have to subdivide or recursively, find the subquadrants, right? We'll be attaching the leaf nodes, I mean the children nodes to it. So what we will do is we will have another, let's say from the top left will be, like I explained to you, right? We have northeast, southeast, northwest, and southwest. So we'll be recursively calling them. This coordinate checking is very easy. We divide that into 4 quadrants, and it would be very easy. We just calculate the midpoint, and for this particular, let's say this grid, the starting point would be this. So I have passed it rightly over there. If you see bottom left, so it will be mid I, as it will be I plus n by 2, which starts from here and which ends over here. So accordingly I've just given the indexes, and at the end, once this all is done, we'll be returning the root. So successfully we have created the quadtree. So basically the aim of this solving this thing is just to explain you how quadtrees are getting used. Okay, so you can give individual try to this particular questions. I know I have not explained it into deep, but that's, it will just give you an idea how we actually use these algorithms in real world systems.
So let's also discuss about some calculations related to quadtrees. So actually, according to our back of the envelope calculations, we said that we'll be having 200 million businesses with us, right? So when we talk about 200 million businesses, we will be having 100. So as I also told you, right, our criteria in general, the criteria would be like 100 businesses in a leaf node, right? So our basically our quad tree would be having 200 million by 100, that is 2 million leaf nodes. Okay, so with this 2, if we have 2 million leaf nodes, there is some reference, mathematical reference, which says that 1 by 3 of the number of leaf nodes are basically the internal nodes of a tree. So let's say if we have a tree, right, and let's say we have 3 leaf nodes over here, so the number of internal nodes, that means root plus, let's say I extend this tree. Okay, so now this all 4 become the leaf node of this tree. Then the number of internal nodes of this particular tree are 1 by third of that. So I know this formula is not depicting over here, but that is there is a mathematical reference to it. So the number of leaf node which I have is 2 million, and 1/3 of it will be 0.67 million. These are the number of internal nodes with us. Okay, so once we have that, we can just do a memory calculation of what is the size of the quad tree is going to be. Okay, so we have 2 million leaf nodes, okay, firstly, and in every leaf node we will be having, let's say, 100 businesses, and let's say one business takes, let's say, 8 bytes. So 8 into 100, that would cost around 800 bytes, plus 32, which is like some metadata for every business we would have. So I'm just keeping 32 for that. So 2 million into 832 bytes would be just for the leaf nodes, and let's say we would have the internal nodes as well, right? So that would be 0.67 million internal nodes. And let's say we just have metadata, we don't have businesses in non-leaf nodes, right, anyways, so it'll be just keeping 32 bytes for just normal metadata. So overall, if you calculate this, it comes out to be 1.71 GB. In modern day world, if we see, this is not a very big issue. It's okay to have like reserve 1.7 GB of memory for something which is going to be useful for us, and also it doesn't it will not let us compromise with any kind of performance with our systems. Okay, so the time complexity to build a quad tree is n by 100 log n by 100. There's again a mathematical reference to it. If you want to go into deep, you can just search it on Google and get to know why it is n by 100 into log of n by 100. And as I already told you, the search time complexity on quad tree is n log n base 4, which is also very pretty much standard. I've already explained to you, because we'll be having 4 children and we will be having n businesses. Okay, so that's it about the calculations on. Yeah, so generally this is the last part of our whole video, where we will be talking about some more deep dives. Basically it is relating to the scaling of the DB and caching. Okay, so when we talk about the scaling of the DB, right, we will be having a business table, right? So obviously this all data of our businesses, which is like 200 million into like the whole the size of each row, that will be good amount of data, and it will not fit on one server. So that's why it becomes a good candidate for sharding, and obviously we'll be sharding based on business ID, so that it ensures that the load is evenly distributed also. So this is about the scaling of the DB, which we can inform about the interviewer as well, that what we are thinking about the DBs and how we can shard them, and how business ID is a good shard key which we can use to shard the database, and that's how the load will be evenly distributed. And then the second thing which we can talk about is caching. And here I also like really don't think that we need a cache, but if at all we need a good read throughput, we can use cache. So mostly the workload is read heavy, and the data set is relatively small compared to like big systems in this case, but the read performance can be a bottleneck, and that's why we can have good number of read replicas, and so that we can improve the read throughput. But if at all we are maintaining a cache, then we would obviously have a geohash key. So geohash, as I told you, that there can be variable lengths of geohashes, right? And for because the length increases with precision. Okay, so we'll be having some geohashes, and for every geohash we can have the list of business IDs ready in our cache, so that what, because we have a query like this, right, which will be firing, where we be getting the business IDs, which is BID, from a geohash index, where the geohash is like whatever this GH is nothing but a geohash given by the for which we are actually finding the nearest neighbors, right? So we'll be getting this kind of query. So it's good to maintain a cache which will be having a geohash, and the value would be, the key is geohash and the value is the list of business IDs, and obviously a business ID as a key. There's one more, key value pair, where we'll be having a business ID as key and the whole business object as the value. So this actually, will increase our whole overall read performance, and also the time to get the response from the query if it's cache, which will be good. But we have to also take care about the cache eviction and updation strategy, which is also an important factor and should be taken care of when we are designing such systems. Yeah, so now that we are done with discussing all the concepts and deep dives of this particular problem statement, we just quickly move on to our functional requirements and non-functional requirements, just to check that we have covered everything or not. So if you see, we have covered all the functional requirements. I'm just giving it a tick once again and seeing if I have not missed anything. We have covered high availability, low latency as well, and the non-functional requirements as well. So once we are done with the functional and non-functional requirements, we just also quickly I want to tell you that it is never that easy going into the interviews when you try to follow the delivery frameworks. Certainly interviewers will have questions in between whenever you write something or whenever you try to explain something. So the overall aim of this video was for you to understand the concept properly. Once you have the concept clarity, you will be able to answer the questions which interviewer is going to ask you in your interview, and when you're trying to follow this delivery framework. This framework is just a mental model which you can have in your mind whenever you are moving into the interviews. And the questions which interviewer is going to ask is mostly checking your concept clarity, which I have tried my best to cover in this particular video.